Welcome to our lesson on radioactive decay, an important concept in physics and geology that helps us understand how elements change over time and how scientists can determine the age of rocks and fossils. Let's start with some basic concepts. A chemical element is defined by the number of protons in its nucleus. For example, carbon always has 6 protons, while oxygen always has 8 protons. Isotopes are versions of the same element that have the same number of protons, but different numbers of neutrons. This means they have the same chemical properties, but different atomic weights. Now, let's talk about radioactive decay. Some isotopes are unstable and will decay over time, transforming into other elements. This process happens when the nucleus changes by emitting radiation. The main types of radiation are alpha particles, beta particles, and gamma rays. For example, potassium 40, which has 19 protons and 21 neutrons, can decay into argon 40, which has 18 protons and 22 neutrons. During this process, a proton in the nucleus is converted to a neutron, and the atom emits a beta particle. The most important concept in radioactive decay is half-life. The half-life of a radioactive isotope is the time it takes for half of the atoms in a sample to decay. What makes this useful is that radioactive decay occurs at a constant rate that is specific to each isotope. For example, the half-life of potassium 40 is about 1.25 billion years. This means if we start with 1,000 atoms of potassium 40, after 1.25 billion years, 500 atoms remain. After 2.5 billion years, 250 atoms remain. After 3.75 billion years, 125 atoms remain, and so on. Let's visualize the radioactive decay process with a graph. The x-axis represents time, measured in half-lives. The y-axis shows the fraction of the original isotope remaining. The red curve shows how potassium 40 decreases over time. Notice how it follows an exponential decay pattern. The blue curve shows the amount of argon 40 that forms as potassium 40 decays. At time 0, we start with 100% potassium 40 and 0% argon 40. At 1 half-life, we have 50% of each. At 2 half-lives, 25% of the original atoms remain as potassium 40 and 75% have become argon 40. And this pattern continues. Now, let's see how we can use radioactive decay to determine the age of rocks. Radiometric dating is a technique used to determine the age of rocks, fossils, and other materials by measuring the amount of parent and daughter isotopes. Let's say we have a rock sample, and we measure that it contains 25% potassium 40 and 75% argon 40. By looking at our decay curve, we can see that this ratio occurs after 2 half-lives. Since the half-life of potassium 40 is 1.25 billion years, we can conclude that the rock is approximately 2.5 billion years old. Let's quickly look at the mathematical formula for radioactive decay. The number of atoms, n, after time t is given by the equation. N equals n0 times e raised to the power of negative lambda times t. Here, n0 is the initial number of atoms, and lambda is the decay constant. The decay constant is related to the half-life by the equation. Lambda equals ln 2 divided by t half, where t half is the half-life. Understanding radioactive decay and half-life is crucial in fields like geology for dating rocks, archaeology for dating artifacts, medicine for using radioisotopes in treatments, and nuclear physics for understanding particle behavior. Thank you for watching this explanation of radioactive decay and half-life.